Hi, in this video, we're going to start to look at electrochemistry, and we're going to talk about electrochemistry in terms of batteries, which we call galvanic cells or voltaic cells. And when we talk about these batteries, or we call those both voltaic cells or galvanic cells, they use a thermodynamically favored redox reaction. And if you'll recall from earlier in the year, redox means oxidation reduction. So a reaction where something is losing electrons and something is gaining electrons. And if there is a favored redox reaction where it's producing a flow of electrons, we can capture that flow of electrons. And that's essentially how a battery works. So going back to that chapter 4 that we did at the beginning of the year, when we're talking about losing electrons and gaining electrons, we use a simple little saying to help us remember what's happening. And that is, Leo the lion says grr. So loss of electrons is oxidation. Gain of electrons is reduction. So Leo, grr. And just a little thing I've set up here also shows you that oxidation always occurs at the anode. And if you just look and see here, if you write out the word oxidation, it has an A, so oxidation occurs at the anode. And if you write out the word reduction, you'll see it has a C. So reduction occurs at the cathode. And so those are a couple of easy ways to determine what's happening where and whether it's oxidation or reduction. Okay. So when we're looking at a battery, we have what's called a cell potential that will help us determine which metal is going to gain or lose electrons. And so you're going to need a copy of a reduction potential table like this. This is just one of them that you might have to refer to. And when you have a reduction potential table like this, the higher the value of your reduction potential, the more likely it is to be reduced. And remember, gain of electrons is reduction. So the higher this value, the more likely it is to be gaining electrons. What kind of substances are favored to gain electrons? Something like fluorine. Okay, fluorine has a high electronegativity value, and so it can easily gain electrons. Something that would have a low potential to be reduced would be something like lithium. And you can see here, lithium has a very, very low reduction potential. It's negative 3.05. And that's because lithium is going to lose electrons. And when it loses electrons, it forms a positive charge. Why does lithium lose electrons? Because it has a low ionization energy. So it can very easily lose those electrons. Okay, so if it has a low potential, reduction potential, it's more likely to be oxidized. If it has a high reduction potential, it's more likely to be reduced. And by looking at this table, you can determine what's happening when you combine two metals together. Okay, so when we look at the example provided here, this is showing an example where we have a battery created with copper and zinc. And the cell potentials reduction values have been provided to you here. You could either look on the table here and find those numbers yourself, but in this case, I've provided these to you. Okay, so copper, when we look at the table, copper plus 2, there's two different coppers. Copper 2 has a plus 0.34. This is copper 1, so copper 1's 0.52. We're looking for copper 2. And we can find it right here on this table. See, I see chromium. Okay, here it is right up here. So copper plus 2 is a 0.34. 0.34, plus 0.34. And then the other element that we're looking here at in this question is zinc. So we're looking for zinc, which is always positive 2. And zinc's going to have a value of 0.76, negative 0.76. So here it is right here. Whenever you're looking at these reduction values, they're showing the half reaction, that's what we call these, in terms of what it looks like if it gains electrons. So all of these half reactions that you're seeing here are showing gaining of electrons. Okay, so if we go back to our example, we have our copper and our zinc. We're able to get those reduction potentials off of our table. And when we look at these, copper has the higher value, and that means that copper is more likely to be reduced. The higher the reduction potential, the greater the potential it is for it to be reduced. If it has a lower reduction potential, it's more likely to be oxidized. Okay, and we know that reduction occurs at the cathode, oxidation occurs at the anode. All right, so when I have my half reaction here, this is the half reaction showing it gaining electrons. So this half reaction is fine as it stands. And the reduction potential is fine as it stands because it is the cathode. It's being reduced. Now the anode is where the zinc is going to be at. The zinc has a low reduction potential, and that means it's more likely to be oxidized. And so because it's oxidized, we need to show it losing electrons. So I need to flip this half reaction to show it losing electrons. And then when I flip it, I also have to make sure that I change the sign. And so instead of a negative 0.76, this is now a positive 0.76. Okay, and then at this point in time, once I have it flipped and I have my value that I need, I can add up the voltage. And then when I add this up, I get a value of 1.1. And so that means that this particular cell, this copper zinc cell, has a value of 1.1. 1.10, that's the voltage. And then once I have my half reactions written correctly, and I'm showing the copper gaining electrons because it's being reduced, and I'm showing the zinc losing electrons because it's being oxidized, I can balance out my half reactions, and I can write out my redox reaction. Okay, so this is my balanced redox reaction. Okay, here's another example I'll show you. So here we have manganese, and this is copper plus 1, and be aware of the charges because they have different reduction potentials. And so these are exactly as you would see them on your table, your reduction potential table here. So they're just like that on the table. Now, when I look at this, I have my manganese has a lower value than the copper. Because the copper has a higher value, that means it's the one that's being reduced. So this one is gaining electrons, and this is reduction, and reduction occurs at the cathode. So I'm going to leave this one alone. And I'm also going to leave the value alone. Now the manganese has a lower reduction potential. That means it's more likely to be oxidized rather than reduced. That means I need to flip this. I need to show it losing electrons. So I need to show the electrons as a product. And because I flipped it, I need to change the sign and now make it positive 1.18. Okay, so once I flip this, I can now add this up. And you have 1.70 as your voltage. Now, when we look at this, if we're going to write our overall redox reaction, if you recall from when we were balancing our redox reactions, the number of electrons that are gained has to equal the number of electrons being lost. And so we need to balance out this. We need to balance out the number of electrons. I have 2 electrons in my half reaction for manganese. I only have 1 in the half reaction for the copper. So I need to double the number of electrons, which will also double the number of copper atoms. Okay, now those balance out. And my balanced redox reaction is 2Cu plus manganese forms 2 copper plus Mn2 plus. Okay, notice I did not do anything to the voltage when I changed the number of electrons. And that's because you can kind of think of this as like temperature or flow of water. It's not going to be dependent on the number of atoms. The voltage is the voltage. It's the energy per charge, not energy per reaction. So we do not have to account for the number of electrons when we balance the equation. Okay, so we will never ever double or triple these values. The only thing that we're going to do to these voltage values is change the sign. And we only change the sign when we show it as being oxidized rather than reduced. Okay, and then just a quick reminder, if this is losing electrons, the manganese is, loss of electrons is oxidation, so the manganese would be the anode, and gain of electrons and reduction, that's at the cathode. Okay, so that's how you find your overall energy of your cell. And that's also how you determine what's being oxidized, what's being reduced, which is the anode and which is the cathode. So you should be able to answer the remaining questions here. All right, the second type of problem that we're going to look at is a problem where you have a cell diagram. And what I've done here is I've provided the same example that we looked at earlier. We have copper +2 and zinc. Now notice this is set up showing the zinc losing electrons and the copper gaining electrons. So copper is gaining electrons, so gain of electrons is reduction. Reduction is at the cathode. Zinc is losing electrons, loss of electrons is oxidation. Oxidation at the anode. And then when you have this positive value, it tells us that this is an energetically favorable or spontaneous reaction. And when you look at these half reactions, what you can see is this. So whenever you have a cell diagram, you always want to show the anode on the left and then the cathode on the right. And what's happening here is this. The zinc is losing electrons, and that's causing it to form a zinc +2. The copper is gaining 2 electrons, the copper +2 is, and that's causing it to form a copper neutral. So a cell diagram would look like this with the anode on the left, the cathode on the right, and it looks like an equal sign in between. And we need to show the flow of electrons for each half reaction. So the zinc to the zinc 2 plus and the copper 2 plus to the copper. So we're showing the flow of electrons. Now we can also do, this is a cell diagram that I've shown you here. We can also do an illustration of a battery. And we have a little bit of space that we can put that. So we're going to draw a picture of these two metals in a battery. And when we're putting these together, we have our two half reactions, and we're going to put those into their separate cells. You can actually make a battery using two beakers. And so I'm showing here, I've got two beakers. And on the left side, I have a solution. And when I have the tin, when I look at my table for my reduction potentials, I can see that the tin plus 2 has a reduction potential of negative 0.14. And when I look at my table, so you're going to look here on this table. When I look at my table here, I'm going to see for the magnesium, I have a reduction potential of negative 2.37. That's what I'm getting off of the table. Because the tin has a larger value, it has a larger reduction potential. So because it has a larger value, the tin is reduced. And because the tin is reduced, it's at the cathode. Okay, the magnesium has a much lower reduction potential, and that means it doesn't have a good potential to be reduced. So therefore, the magnesium must be oxidized. And oxidation occurs at the anode. All right, so I'm going to make my two half cells, and I know that my magnesium is at the anode. I'm going to put the anode on the left, so I'm going to label this my anode. And I know that magnesium is at the anode. Now, when I write my half reaction for the anode for magnesium, I need to show it losing electrons. So the half reaction should clearly show the magnesium losing electrons. And actually, it already is. And because it's losing electrons, if you'll recall, we flip this number, we make it positive. So the reduction potential is negative 2.37, but the oxidation value is positive 2.37. So in my beaker, where I have my anode, so my anode beaker has a solution of magnesium ions. And then it also has magnesium metal. So there's a strip of magnesium metal. So your battery is going to have two half cells. Each half cell is going to have the metal electrode. Because magnesium is my anode, the electrode on the anode side is magnesium metal. Because this is my cathode, the side where I have the tin, my tin strip of metal is my electrode on the cathode side. And then I also have my solutions in the beaker that allow that flow of electrons. So on the magnesium side, I have magnesium 2 plus. On the tin side, I have Sn 2 plus. All right, and then between these, I'm just going to move this out of the way. Between these two beakers, I have what's called a salt bridge. Now, the salt bridge has to be some sort of a soluble ionic compound. And the purpose of the salt bridge is to prevent a buildup of negative charges on one side compared to the other. And so that's the purpose of the salt bridge here. Attaching the two metal electrodes, we have a voltmeter. And the flow of electrons goes from the anode side over to the cathode side. So the magnesium is being oxidized. It's losing its electrons. So the electrons are flowing from the anode side over to the cathode side. Okay, so your electrons in a galvanic cell will always flow from the anode side over to the cathode side. This side's being oxidized. Loss of electrons, oxidation at the anode. This side is gaining electrons. Gain of electrons is reduction at the cathode. Now, on the cathode side, because it's gaining electrons, we need to write the half reaction showing that it's gaining electrons. And so Sn 2 plus gaining electrons forms Sn. So all I had to do is take this half reaction that you see here and just rewrite it, showing it gaining electrons. And because it's gaining electrons, it has a higher reduction potential. And so that was negative 0.14. Okay, so as these electrons flow over, and usually what we have in the solution will have something like magnesium nitrate. So you'll have this little spectator ion here, which will not impact your flow of electrons here. So you have this spectator ion. Generally, we don't even write it because it's not going to impact anything that's happening here with the flow of electrons. What will impact the flow of electrons is the salt bridge. So if I have all of these negatives traveling over to this side of our battery, our galvanic cell, over time, you're going to have all these extra negative charges on our cathode side. And so you're going to have a buildup. And so the purpose of the salt bridge is it allows a flow of positive ions into the solution to balance out this buildup of electrons on this side. So the positive ions will flow from the salt bridge onto the cathode side. And on this side's losing negatives. And so the salt bridge will replenish those negatives by sending out the negative ions on this side of the salt bridge. So for instance, if you had sodium chloride, the sodium ions would flow to the cathode side to make up for all those electrons flowing over to the cathode side. And the chlorine, if you had sodium chloride, that would flow out to the anode side to make up for all of those negatives that are being transferred over. Right? So it has to be a salt bridge, has to be something that's soluble, that will not react with the anode or cathode electrodes. Okay, and so when you have the salt bridge, if you don't have a salt bridge, the voltage will drop to 0. So the purpose of the salt bridge is to keep that voltage from dropping. It makes sure that we do not have a deficiency of negative charges or a buildup of negative charges. Okay, so this is my illustration of a battery, a galvanic cell. And if I were to take my numbers here, we said that we flipped this. It had a negative 2.37, and we said that it was losing electrons instead of gaining electrons. So we flipped that sign. Instead of negative 2.37, we made it positive 2.37. And then on our tin side, this was negative 0.14. Okay, when we add this up, this is going to give us our cell potential. And so we take positive 2.37 and negative 0.14. And that gives us a cell potential of positive 2.23. And so this is our energy of our cell potential. Now, if your cell potential is greater than 0, we say it's a spontaneous reaction. It's thermodynamically favorable. So this is thermodynamically favorable, which tells us it has what we call a Gibbs free energy. That's a negative value. Gibbs free energy is essentially the free energy when you look at reactants compared to products. So if it has a negative Gibbs free energy, the reactants have more free energy than the products. Okay, so the reactants have more free energy than the products. That's why it's a spontaneous reaction, because the reactants have more free energy. And that gives it, we'll talk more about Gibbs free energy in following lessons, but the Gibbs free energy will be less or be greater than 0. I'm sorry, it'll be negative. And because it's a negative value, we call this an exergonic reaction. Okay, we'll also talk about that later. So that's something to look forward to. All right, so that's how you do a cell illustration, and that's how you do a cell diagram. Okay, let's just do one more for practice. Okay, so here we have aluminum and we have magnesium. And we're going to draw our illustration for this. We're going to show what is oxidized, what is reduced. We want to make sure to include the salt bridge. We want to make sure we show the flow of electrons and label our cathode and anode. And then we also want to indicate if this is a thermodynamically favorable reaction. Okay, so we're just going to start by getting these values off of our table. And we're going to start by finding the value for aluminum. So when I look at my table, and you'll also have a copy of one of these tables, when you look at the table for aluminum, you're going to see that aluminum has a value of negative 1.66. Okay, then we look at magnesium. Magnesium has a value of negative 2.37. Okay, the more likely it is to be reduced, the higher the reduction potential. So aluminum is actually more likely to be reduced. Okay, the magnesium has a lower reduction potential, so it's more likely to be oxidized. Okay, now I'm going to give a little bit of space over here so we can do both. Okay, so I have my anode side and my cathode side. And I have my two half reactions. And I'm going to put the anode on the left. I'll put the cathode on the right. Inside of my beakers, I have my solutions. And then I have my electrodes. Okay, and this is my salt bridge. It's going to be some sort of a soluble ionic compound. Sodium chloride would be a great choice. And then the anode, so we said the aluminum is gaining electrons. And so reduction occurs at the cathode. So the cathode side is the aluminum metal and the aluminum ions in solution. So if this was aluminum nitrate, okay, and these will be spectators. And then you have your aluminum electrode. Okay, so on the anode side, so losing electrons, oxidation is at the anode. So the anode side is the magnesium. And your solution has the magnesium ions. Could also be magnesium nitrate. Okay, but these will be spectator ions. And then connecting the two half cells, we're going to have our voltmeter. And the flow of electrons is from the anode side to the cathode side. So the magnesium is being oxidized, so it's losing electrons. And the aluminum is gaining electrons. And so that's on the cathode side. All right, because the electrons are flowing over to this side, this is our negative side, then you're going to need some sodium ions flowing out into the solution to balance out those negative charges that are adding up. And then because the anode side is losing electrons, you're going to have some chlorine ions flowing out from the salt bridge to replace those negative charges. All right, so we need to show the aluminum gaining electrons. So we need to write our half reaction showing it gaining electrons. And the magnesium side, we need to show it losing the electrons. All right, because the aluminum is gaining electrons, we're going to keep our reduction potential. Don't change the one that's being reduced. Don't change the number. Now, the magnesium isn't actually being reduced, it's being oxidized. So the number isn't negative 2.37, it's positive 2.37. The reduction potential is negative 2.37, but the oxidation potential is positive 2.37. Okay, and then now once we have these values, what we can do at this point in time is we can give our cell potential for this reaction. And so we're going to add up our values here, and that's going to give us our cell potential. That should be 0.71. Now if we're going to do a diagram, so this is an illustration. For our diagram, we want to do the same process. We want to show the anode side and the cathode side. And so the magnesium is the anode side. So on the anode, magnesium loses electrons. to form magnesium 2 plus. The electrons flow from the anode side to the cathode side. On the cathode side, the aluminum ions gain the electrons to form aluminum metal. Okay, so basically it's taking this illustration that we did here and it's putting it into a shorthand form that we call a diagram, cell diagram. All right, so you should be able to answer up through number 7. And when you're answering each one of these, just a heads up, when we say that this is a positive E of our cell, we're saying that this is a favorable reaction, so it's spontaneous, and that's going to mean that our delta G is less than 0, our Gibbs free energy. And like I said, we'll get into more of that later, but as long as you have a spontaneous reaction, your delta G is less than 0. And so make sure you indicate that when you do questions 6 and 7. Right now, all of these values that we're taking off of our standard reduction table, it'll tell you on the table that these values are at 25 degrees Celsius. And so we're assuming that these are standard conditions when we're doing these types of reactions. Now, sometimes you will have conditions that are not standard. And in that case, we're going to use Le Chatelier to determine if it will be a spontaneous or non-spontaneous process. Okay, so we're going to do an example here. Okay, so let's say we have these two half reactions. We have a tin +2 and magnesium galvanic cell. So the first step, what we're trying to figure out if we add some SN2+, how does that affect the voltage of this battery? And the first step to doing that is by writing your balanced redox reaction. So we need to write out our balanced redox reaction. And before we can do that, we need to take our numbers off of the table. So when I find tin +2 on my reduction potential table, I see that tin +2 has a negative 0.14 voltage. And I see that my magnesium is negative 2.37. So the tin has a greater number. So that means a higher value than magnesium. So that tells us that the tin is being reduced. It's more likely to be reduced because it has a higher reduction potential. The magnesium is more likely to be oxidized because it has a lower reduction potential. So when I write my half reaction for the tin, I need to show it gaining electrons. When I write my half reaction for magnesium, I need to show it losing electrons. So the electrons should be on the right. Okay, now I'm going to take my two half reactions and bring them together just like we did when we were balancing redox reactions. The number of electrons balances out. So I'm actually going to write these right over top of each other. I can add these up, and that gives me tin +2 plus magnesium. I'm just writing a balanced redox reaction. Gives me tin plus magnesium +2. Okay, so this question is asking, will the reaction go to the left or the right, and what happens to the voltage if we add SN2 plus. So if we add SN2 plus, we're adding more of this substance right here. And anytime you add something, according to Le Chatelier, it goes away from what's being added. So it's going to go to the right. That pushes the reaction to the right, which will increase your voltage. So as long as it goes to the right, that increases the voltage. Now, if I were to add magnesium, the opposite would happen. It would go to the left, and that would decrease voltage. So as long as you can push that reaction to the right, then you increase your voltage. If you push it to the left, it decreases the voltage. Okay, so you should be able to do 8, 9, 10, and 11 from here. All you have to do is write your two half reactions. Make sure you show the one that has the higher reduction potential gaining electrons, the one that has the lower reduction potential losing electrons because it's being oxidized. Balance out the number of electrons and bring them together, just like we did on the very first Electrochem handout. Okay, now you can also use half cells that have the same exact elements and the same exact solutions. So for example, let's say I have two half cells and they both have zinc and they both have zinc nitrate. And we can show them attached by the voltmeter. The voltmeter captures the flow of electrons. And then we can also put in our salt bridge. Okay, so what we have here, we're being told that we have two zinc nitrate solutions and they have different concentrations. So let's say on the left-hand side, I have a zinc nitrate, and once again, you don't have to put the nitrate, but let's say we have a zinc nitrate concentration of 1.0 molar. Unless you've been told otherwise, you can assume the concentration is 1 molar. Okay, let's say that we have the same exact half cell, but in this one, we have, instead of a concentration of 1.0, it's 2.0. Okay, what does that mean to us? This side has more Zn2 plus because it has a higher concentration. That means there are more positives on this side because we have more positive ions. We have twice as many of these positive ions because we have twice the concentration. And so because we have more Zn2 plus, the electrons are going to flow over in this direction. They're going to be attracted to all of these positive ions over here. So this will actually force a flow of electrons from a lower concentration side to a higher concentration side. And then just a heads up, it's always 1.0 molar unless indicated. Now, because this side is losing electrons, loss of electrons is oxidation. Oxidation is at the anode. That means the lower concentration side is the anode. and it makes the higher concentration side the cathode. Okay, so you should be able to do 12 and 13 now. And once you've completed all of these, I can post a key for you so you can go back through and check your work.